Hi, everyone. So today we'll be going over some problems that use BFS and binary search. They're topics we've covered in the past, and we'll practice them some more. So the first problem we'll be doing is grid jumping on Caddis, and the link is in the chat. And I'll go ahead and share my screen so you can see it there as well. And I'll give you a minute or so to read the problem before I go ahead and explain what it is. You guys can see the screen, right?
Yeah.
Okay. We'll be coding the first two problems together. So this would also be a good time to open up IntelliJ, REPL.it, whatever you use to code. And then for the remaining problems, we'll discuss how to solve them because we don't have enough time to code all of them together. So hopefully everybody's been able to take a look at this problem. In this problem, you're given a grid and you start in the top left corner. Your goal is to get to the bottom right corner. Each of these numbers tell you how far in the grid you can jump. So if you take a look at this example we have over here, we started this top left square, and the 2 tells us that our jump distance is 2. So we could jump 2 squares up, we could jump 2 squares to the right, we could jump 2 squares down, or 2 squares to the left. And once again, our goal is to get to the bottom right corner. So in order to do this, we have to use a BFS. Well, that's what we actually talked about a month ago. So I think I should probably review BFS and binary search before we go into the problems. Yeah, so we'll start with the BFS and we'll just do a quick review of what these algorithms are for people who weren't able to attend those meetings or may have forgotten. But a BFS is just an algorithm to travel to a grid or graph. So you have a starting point, so like this point over here. And the way that the BFS works is it travels to the points that are closest to your starting point, and it goes outwards from there. So first, our BFS would visit these 4 squares over here where I've drawn these circles, because they are only 1 unit away from our center starting point. After going to those 4 squares, the BFS would expand outwards to these squares, which are 2 steps away. Like I've drawn slashes in them. And then it would go to squares that are 3 steps away. I've drawn X's in those. And it'll keep on moving outwards until it's visited all the squares. So that's what a BFS does. As for a binary search, a guessing game is a good example of that. Basically, we have a range of numbers where our answer lies. So we have this range of numbers where our answer is inside of. And instead of guessing each of the possible numbers one by one, which takes really long, what we'll do is we'll try the number in the middle. And then if that number is too low, then we'll look inside this range over here. Otherwise, we'll look inside the lower range. And what this does is each of our guesses cuts the search space in half. So initially we had to search for this, we had this whole range of numbers, maybe from 1 to 100 of what the answer was. By guessing 50, if they were to say if 50 is too high, now we can discard this area. We don't care about that. We only need to search the numbers from 1 to 50 because they told us 50 was bigger than their number. So we only need to search from 1 to 50. And if we keep that, it cuts the amount of space for your search in half, which is much faster than trying every single possible combination. Are there any questions about that? About any of those two topics? I know it's a quick review, but now that we've covered it in past meetings, we're going to solve some problems using them. Okay, if there are no questions, so we'll go back to this grid problem and I'll post the link into the chat.
Madhu, you did. Yeah.
Okay, thank you, Madhu. Yeah. So coming back to this problem, we have this grid of squares and each position tells us how far we can jump. So for example, we start in top left square, we want to get to the bottom right one. And in this top left square, we have a jump distance of 2. So we can jump 2 squares up, to the left, down, or to the right.
Or
You
just
can see this is the answer that they've outlined for us over here.
I tried to get this on mute. Unmute.
Okay, yeah, so you can see the answer over here. The answer is to jump 2 squares to the right. So we come over here. Now that we're at this square, we jump 2 squares down. Now we're on a square with a 1, so we can only jump 1 square to the left. We're once again on a square with a 1, so we have to jump 1 square up. Then we can jump 2 squares to the right, 3 squares down, and now we're at our answer. And the problem is we have to find the shortest number of jumps we have to take to go from the top left corner to the bottom right corner. And if it's impossible, we have to print -1. So this seems like a pretty daunting problem if you don't know BFS, because otherwise it'd be like, how do you do this problem? You don't just move one step at a time. It's based on which square you're currently at. Because we're at this square with a 2, we can jump a distance of 2. So another possible path may be to jump 2 squares down and then 3 squares to the right. Well, no, actually that wouldn't work. Yeah, this is the only possible path. But for some other problems, for some other test cases, there may be multiple ways to get to the end. But we want the shortest one. So does everybody understand this problem of starting in the top left corner and then we want to get to the bottom right and print the shortest number of jumps? Are there any ideas for how we can do this? Think back to our original BFS. So once again, with our original BFS, we visit squares based on how far they are from the initial starting point. And in a regular BFS, we just have a jump distance, you could call it, of 1. So what happens to our jump distance over here for this problem? Is our jump distance always going to be 1? Our jump distance, yeah, that's right. It's not going to be 1 all the time. Our jump distance is based on what the number is in the square. So the idea behind this problem is we'll look at the current number we're at, and then in a traditional BFS, we would add the neighboring squares to our queue. And a queue is what we use to keep track of which squares we should go to next. So instead of adding the squares next to us in our queue, like these two ones over here, we'll add the squares that are 2 steps away because our jump distance is exactly 2. That's what this 2 over here tells us. So we add these squares, and then from this square, we would add this square again, and this square, and so on. So that's the modification we have to make to our BFS. And now we'll see how to code it. It'll probably make more sense once we start coding it because there isn't too much to discuss. So that you guys can go ahead and pull up whatever you use to code. And over here, I have this over my Java class open over here in IntelliJ. And BFSs are quite wordy. They require quite a bit of typing. So I'm going to go through this a little fast. If at any point you want me to slow down, just let me know. And then I can take some time to slow down and explain what I'm doing. Okay, so let's get started. So the first thing we're going to have to do in any problem is read in the input. We'll use a scanner to do that. So scanner sc equals new scanner system.in. Then you can see they're giving us 2 numbers as input. The first one is the number of rows. So over here we have 5 rows. The second one is the number of columns. So we'll have int rows equals sc.nextInt, int columns equals sc.nextInt. Now that we have this, we will also have to read in this grid. So we will do that with a 2D array, which Madhu and Kanishk have covered. So we'll have a 2D array, and the number of rows we'll have is our rows variable. The number of columns will be the columns variable. We'll also move our scanner to the next line because right now it's still on the first line. There's an end line character, so we just want to say sc.nextLine. Now for actually reading in our input, this is what it's going to look like. First, we're going to iterate for the number of rows we have. This is what the for loop does. It goes from 0 up to the number of rows minus 1. And you can see that they haven't given these numbers separated by spaces. So if we did int number equals sc.nextInt, it would give us 2120, which is not what we want. We want to read in each of these digits individually. So what I'll do is I'll just read it into a string. I'll read that row into a string. So I'll say string line equals sc.nextLine. And then I will go through the string. The length of the string is the number of columns there are. So over here, there are 4 columns. So that's why I have a for loop going through the number of columns. And over here, I will say grid of I of j equals integer.parseInt. because right now it's a string. I'll say line.char at j, and then this needs to be a string. I can't see because of zoom. Wait, let me zoom out a bit. And there. So this will be how we read in our input. I'll copy and paste this into the chat so you guys can also take a look at it. Are there any questions about this part so far? So this is our input. Now we're going to go into the actual BFS, but before we do that, there are some things we need to keep track of. So how do we keep track of the squares that we need to visit? What data structure do we use? Does anyone remember? It starts with a Q.
Q.
Yeah, that's correct. We use a queue to keep track of the squares we have to visit. So we'll have a queue over here, but because this is a 2D grid, we have to create our own coordinate class in order to add the squares there. So we'll quickly create our own coordinate class, and it will have a row number and column number. We'll have a constructor. Um, And the constructor will take in the row number and column number. So say row equals R, col equals C. If you haven't taken APCSA and you're not too sure what this does, you don't need to worry about it too much. Whoops. This is basically so that we can have our queue store coordinates instead of integers. And I'll also paste this into the chat. And don't worry, you don't need to write Java docs for the constructor. Okay, so now we have this coordinate class and we can have our queue of coordinates. I'll call it Q. And this will be a new linked list. So we have our queue. And who remembers what else we need for our BFS? So we obviously need a queue to add our squares that we have to go to. We also need a Boolean array. And does anybody remember why we need a Boolean array and what it's used for?
To track whether you visited it or not.
Yeah, that's correct. We need a Boolean array to keep track of whether we visited a square or not. So if we start over here, let's say we add this 2, right? So now we add this 2. Sometime later, we go to that 2 and we say, okay, we can add this square because it's 2 steps away. We can also add this square. But the problem is we've already been to this initial square. That's where we started at. And we don't want to go to that square again. Otherwise, we'll get caught in an infinite loop. So that's why we'll have a Boolean visited array. This will also have the dimensions for this will be rows and then columns. And that's our Boolean visited array. And the last array we need, if you remember, we covered this in the BFS meeting. In order to count the number of steps that it takes to reach a particular square, we're going to use a 2D int array. So you can see over here, this is the code that we posted a while ago from our last BFS meeting. And we use a 2D int array to keep track of how many steps it takes to go to a position. So I'll have a steps array, and this will also have dimensions of rows, columns. So are there any questions about the code so far about this visited array and the ints array? So for example, steps of I of j will tell us the number of steps it takes to go to I, j. That's all this is. And visited will tell us whether we've already been to a square or not. Now, because we want to find the shortest number of steps to reach a position, that's what we're interested in, we'll go ahead and set the steps array to be a really large number initially. So we'll say for int row in steps, we'll say arrays.fill row with a really large number. And the reason for this is because there are multiple ways to reach a square. So let's take a look if we can find a specific example. Yeah, so I can't find a specific example from here. There probably will be one, but I'm not going to spend the time. But the reason we're doing this is because there are multiple ways to reach a square. So let's just choose this square, for example. Maybe there are 3 different ways to reach it. Maybe one way is taking only 2 steps, another way is taking 5 steps, and another way is taking 10 steps. We're only interested in the way that takes 2 steps because that's the smallest amount. So that's why initially we'll set these with a really large number, and then we'll take the minimum of the number of steps that it takes to get there that we've calculated and what's currently there. So now that we have this, we can go ahead and start our BFS. We'll say q.add new coordinate 0, 0. The reason we add 0, 0 is because that's where we start from. And because we also start from this, the number of steps it takes to reach 0, 0 is equal to 0. So we have those two things there. And now we're going to go while our queue is not
Someone wants you
empty.
to slow down a little in the
What?
chat. Someone wants you to slow down a little in the chat.
Yeah, sure. Do you want me to copy and paste the code I have? We do have some more problems to get to, so if it's a problem of typing what I'm typing, we can put this up on GitHub later. Oh, looks like I can't copy and paste it. It's too large. Okay, this is getting really laggy like last time. Okay, looks like it. Wait,
This is
thank you,
the
Madhu.
code in the chat.
Thank you. Cool. Okay, so now we'll go while our queue is not empty, and we'll take our top coordinate. So we'll say coordinate currently at equals q dot pull. So if you remember, the first element in our queue will be the coordinate square that we're currently at. And what q.poll does is it gives us that coordinate and it also removes it. So now what we'll do is, yeah, so we have this top coordinate. And over here, we will check if we have visited currently at dot row and currently at, whoops, this is too laggy. Currently at dot call. This basically means we've already been to this square. So we've already been to the square. So what we want to do is check if this is if we've already been to the square, we want to check, well, if we've already been to the square, we want to continue because we don't want to go to it again. This will just continue in our for loop. If we haven't been to it, then we want to say currently at dot row, currently at dot column. We will set that to true. So that's what that does. If you've been to a square, continue onwards. We don't want to go visit it again. If you've not been to a square, well, we're currently at it, so set it to true. If you also remember from last time, we had, in order to actually make our jumps, we had 2 arrays to keep track of how much we had to change our x and y by. We'll do that again. If we want to move up, we have to decrease our row number by 1. To move to the right, we don't change our row number, so that's why I'm typing 0. If we want to move down, we increase our row number. And if we want to move to the left, we have to not change our row number. I'll just copy this and do the same thing for y. And over here, if we want to move up, we just change our row number. We do not change the column number. If we want to move to the left, we increase our column number. If we want to move down, we don't change our column number. And if we want to move to the left, we decrease our column number. So now what I'll do here is I'll go through each of these 4 directions that I can go through. So for int d equals 0, d is less than 4, d plus plus. I'm going to say new row. So this is the new row. And I'm going to have 2 variables for the new row and column that I'm going to move to. So new row is going to be equal to, who knows what the current, how do I get the current row that I'm at right now? I'll give you a little hint. It has something to do with currently at. How do I get the row number of currently at?
Would it be currently at dot row?
Yeah. So I'm going to say my new row is going to be equal to currently at dot row, because let's say for our initial example, currently at dot row is 0 because that's the row number we're in. So we want to calculate our new row if we wanted to move downwards, for example. So we're going to say 0 plus, how do I get the jump distance of this position? Remember, I have a 2D array that stores the jump distances. It's called grid. How do I get the jump distance for this specific position that I'm currently at?
You would do grid at currently dot row, currently at dot column.
Yeah,
to
that's
get
correct.
the jump distance.
Yeah. And the reason we're using 4 over here is because there are 4 directions that we can go in. These are our 2 direction arrays, and we'll be using them now. So int new row is going to be equal to currently at dot row. And over here, I'll have a variable called jump distance. So jump distance is going to be equal to grid currently at dot row currently at dot call. And this jump distance variable basically tells us how far we can jump from our current position. That's why we're also using this grid array over here to get how far we can jump at our current position, which is row comma call. And what we're going to do with that jump distance is multiply it by dx of d. So for example, dx will initially, the first value in our array dx is -1. So let's say we were over here and our jump distance is 2. So what's going to happen is it will multiply this 2 over here by -1, and it will add it to our row number. So right now our row number of this 2 is 3, 0, 1, 2, 3. And it will take 3 and add -2 to it, and this will take us 2 squares up. Does everybody get that? That's why we have this array with negative numbers, zeros, and that's why we're also doing multiplication over here. It just makes it a lot faster to go to squares rather than having to hard code, go to this position plus this value, and then do that 4 times. We can use a for loop instead to do that pretty neatly. So that's what this is doing over here. We're going to copy the same exact thing, change it to new column, because we also need to know the new column we're going to go to. And then we'll say currently at dot call jump distance, and we'll change that to dy. So now we have our new row and new column that we're going to be going to over here. Before we actually add this new square with coordinates new row, new call, we have to check whether it's in bounds. Because if you remember, if we start over here at this first square and our program does 0 minus 2, which gives us a row number of -2, row -2 doesn't exist. And it's going to give us an error if we try to go to that position. So in order to deal with that, we'll create a Boolean method outside of our main function. So I could say public static boolean in bounds int I, int j, int row, int call. This will basically take in 4 numbers. The 4 numbers we'll take in is I and j, which is our current position. It will also take in row and column, which is the number of rows and columns in our grid. So if something is in bounds, if I is greater than or equal to 0, j is greater than or equal to 0, j is less than calls, and I is less than rows. Okay, that should be call. And I'll copy and paste this into the chat. Oh, that's the wrong thing. There. Okay, so what we'll do over here is check if this new row and new column is in bounds, and we'll pass in our row and column variable. If it's in bounds, oh, it's called rows and calls. Yeah. So if it's in bounds, we want to visit it. But for this particular problem, we also have an extra condition we want to check. We only want to go to a square if we found a shorter path to it. So let's just choose a random square. This may not be true, but I'm just going to choose this random square. Let's say we do our BFS, and then our program finds that there are 3 ways to reach this square. It takes 3 steps to reach this square. And let's say later on it comes across that same square and it finds that there are 8 steps needed to reach that square. Which is smaller, 3 or 8?
3.
Yeah. And if we want to find the shortest number of jumps it takes to reach a position, should we use that 3 or should we use that 8?
3.
Yeah, if we want to use that 3. So what we'll do over here is we will only visit a square if it's in bounds and the number of steps it takes to reach that square of steps it takes to reach that square. So steps of new row, new call is greater than steps of currently at. I know this is getting really verbose, but currently dot call. I can't see because of Zoom, but okay, that looks, yeah, +1. Yeah, part of the reason it's so long is because our variable names are pretty long as well. I wanted this to be able to be easily read. So there, I just copied and pasted that if statement. So that's the condition that has to be met in order for us to go to a new square. And when we want to go to a new square, we'll say visited of new row and new call is false. Because if this is not false, it's going to skip that square later on. We want to set it to false right now so it doesn't skip that square. We also want to add it to our queue. So queue dot add new coordinate. This is where we create our new coordinate using the new row and new column we calculated. And the last thing we're going to do is update the number of steps it takes to reach there. So steps of new row, new call equals steps of currently at dot row, currently at dot call +1. Yep. And then what we'll do over here, so this is our BFS. I'll explain what this whole code does in a minute because I know it may be a little hard to follow along. But over here, now we're done with our BFS. And before we print our answer, there are two different types of answers we have to give. One is whether it's even possible. One is whether it's impossible to do it. So in this example, you can see we have this 2x2 grid, and we can only take jump distances of 2, which takes us out of bounds. It's impossible to reach this last square. So that's why over here, we're going to check if we have not visited rows -1, calls -1. Who can tell me what rows -1, calls -1 is the position of? Rows is the number of rows, columns is the number of columns. What is rows -1, columns -1?
Oh,
That's the bottom right square.
Yeah, that's correct. It's the bottom right square. So we're going to check if we've not visited this bottom right square, that means it's impossible to do it because our BFS couldn't reach it. Otherwise, we're going to print out the number of steps it took to get there. And this is our this is our answer to the problem. So I'll just quickly go over what it does. This is just the input stuff, not really important. Over here, we want to initially set the steps array with really large numbers because we want to find a minimum distance. This is how much we have to change our row number and column number by. We're going to iterate while the queue is not empty. The top element of our queue, so currently at, is the square we're currently at. So initially, currently at will be a coordinate 0, 0, which is what we added to our queue. We're going to check if we've already visited this position. We don't want to go to it again. So we're going to continue. If we've not visited, we're visiting it now. So we set it to true. We also have our jump distance over here, which is how far we can jump at our current position. Grid is the 2D array that stores these numbers over here we got from the input. And that's where we have grid currently at dot row, grid currently at dot call. We iterate through each of the directions that we can move in. We calculate our new row and new column using our current position, as well as our jump distance. We check whether the new position is inside of bounds, as well as if we found a shorter path to it, because if the path we found to it right now is longer than something we found earlier, there's no point in doing it again. And then over here, we just add it to our queue, calculate the new number of steps. This is our output to check if something's not visited, it's not possible. So we print -1. Otherwise, we print out number of steps. And we can just go ahead and run this, verify that it works. And we got 2, which is correct. We'll copy the second test case, run that. We get -1, which is correct. And we will run this as well. And we got 6. So this is the solution to this problem. Once again, it will go up on GitHub. And the recording is also going to go on YouTube, so you can come back to it later. Are there any questions about how this works? You can see it's pretty wordy. Okay, good. Yeah, this is a little this was a kind of hard problem to choose for the first problem for this meeting. The next one will actually be easier than this one. And I'll post the link to that. So we'll go on to our second problem, which is going to be a binary search problem. And we'll give you a minute to read it, and then Madhu will go over the solution. Here, you can also read it on my screen. Okay, so hopefully everybody has had enough time to read this problem. If not, that's fine. So basically in this, oh wait, Madhu, you can go ahead and explain it.
Yeah. So for this problem, I mean, I'll just explain it again because I don't think there's enough time to read it. But if you can go back to the problem.
Yeah, I'm going to.
Okay. Yeah. So you're given a location of a bunch of hay bales, and as you can see, it's kind of like in a number line, and that is like the location of these hay bales, and that is on the second row. So in the first row, the sample input, the number 4 represents the number of hay bales that were B, and the number 6 represents the number of coordinates we kind of have to search through. So we have after our second row, which is the number of hay bales, we're given these minimum and maximum coordinates. And what we need to do is we need to find out how many hay bales are between those minimum and maximum coordinates. So to go over the sample output for 2 and 3, it would be 2 because the hay bale at coordinate 2 and the hay bale at coordinate 3, 1 plus 1 is equal to 2. So if we go to the next one where we have 2 and 4, there's still going to be 2 because the only hay bales that are between 2 and 4 are hay bale at coordinate 2 and hay bale at coordinate 3. And we do this for all of our test cases. So I'll just go over each of them to make sure you guys understand this. So for 2 and 5, we have our hay bales at 2, 3, and 5. For 2 and 7, we have all of our hay bales. And I'll just let Ishan show that. Yep. And then for 4 and 6, we're going to have our hay bales at 5 and only at hay bale 5 only, because 5 is the only number that's between 4 and 6. And then for the last one, we have 8 and 10, where there'll be no hay bales because there's no hay bales that are between 8 and 10. So you're given, initially you're given these numbers 3, 2, 7, and 5. And what we could do is we can put this into an array where we can then run a arrays.sort, and then we can sort that array to get this kind of number line to have because when the numbers are sorted, it'll be a lot easier to work through it. So when you have it sorted, it'll be 2, 3, 5, and 7. And there are some ways to go through this problem. The first way that might come to your head is going through every single number and checking if it's within the minimum and maximum, which is not the right solution. Because if you go up in the problem, there could be potentially 1 billion hay bales, and that's going to take a really long time to go through every single one of them. So we don't want to do a linear search because that's going to take a year to run through the whole program. So another way we can work through this problem is we could identify what index is that minimum coordinate at, and then what index is the maximum coordinate. So to give an example of what I'm saying, we have our test case of 2 and 3 as our minimum and maximum. If we were to look at that test case of our minimum number is 2, you can see it in our actual grid. The answer would be like index 0 because 2 is equal to 2, so we'll be at 0. And then for 3 is at index 1. So we have our maximum index of 1 and our minimum index of 0. And if we subtract 1 minus 0, we would get 1, and then you want to add 1, which will get 2, and that's how you get your answer 2. And I'll go over a few more cases to kind of clarify what I'm saying. So next we'll go over 2 and 4 for our minimum and maximum. So we're going to find the number that's closest to the number 2, and that is the 0th index, which is that first 2 Ishan is underlining. And for number 4, we don't want to go to 5 because if we end up going to 5, that's past the maximum. So we want to go back down to 3. And that'll be our index 1. And then we'll do index 1 minus 0, we'll get 1. And then we need to add 1, or we'll get 2. I'm going to go through one more example with the number 5, or 2 and 5. So once again, the number that's closest to 2 is at index 0. The number closest to 5 is at index 2. 2 minus 0 plus 1 will get our answer of 3. So now we need to think about how are we going to get these numbers that are closest to the minimum and maximum points that are in the sample input. What we could do is we could use binary search to find these numbers really quickly without having to go through every single number. Because our array is sorted, it'll make our binary search a lot easier to run through. And by having an array sorted, you're able to do the binary search.
Yeah, so that's a really good explanation, Madhu. Everybody gets the problem, right? Just given some hay bales, and you want to find how many hay bales are between 2 coordinates. For the sake of time, I've already written the input I've written the code to read the input for the problem. I've just pasted that into the chat so we can go ahead and get started immediately.
Sure. I have a question.
Yeah.
Could we do like a sliding window approach? Do you know what that is?
Yeah, I know what it is. No, that would be too slow though.
Oh, okay.
Yeah, that was a good question because there are 100,000 numbers and there are, let's see. Yeah, there are 100,000 numbers and the number of queries, how many queries are there? The next queue lines. Oh yeah, there's also 100,000 queries, so it'd be too slow. We'd have to do a binary search and log n.
Okay.
Yeah, so this is our input over here. N is the number of hay bales. Queries is the number of queries. Bales is our array that contains these numbers over here. These are where the hay bales are located. Like Madhu said, this is really important. In order to do a binary search, you have to have a sorted array. So the first thing we're going to do is say arrays.sort, pass in this bales array, and now we have a sorted array. So this will look like 2, 3, 5, 7 for the first example. Now what we'll do is we'll iterate while we have more queries. So we'll say while queries minus minus is greater than 0. What we'll do over here is we will go to the next, we'll put our scanner onto the next line, and then we'll read in our left and right bounds that they want us to answer. So if you look at this first example, L and R would be 2 and 3. And they're basically telling us they want us to find the number of hay bales between coordinates 2 and 3, which as you can see, the answer to that would be 2. Now, this is just pretty much a basic binary search that we also covered in one of our previous meetings. The code is going to be almost exactly the same. We could copy and paste it, but I'll just quickly write it from scratch. So what we need to do our binary search is have a lower bound and an upper bound. I like to call those low and high. So low will be equal to 0. High will be equal to n minus 1. We will also have a lower bound and upper bound for our answer. So lower bound equals n, int upper bound equals 0. This will basically tell us the indices of our answer, of where those hay bales lie. So for example, if they told us how many hay bales are there between coordinates 4 and 6, lower bound would be located at where the 5 is, because that's the smallest number bigger than 4. Upper bound would also be located at the 5 because that is the biggest number smaller than 6. So now with our binary search, we're just going to go while low is less than equal to high. And this is, yeah, like I said, the same thing as last time. So we find the number in the middle by doing mid equals low plus high divided by 2. And then we check if the hay bale at this position is farther to the right than the L, than what they want us to find, the lower bound for what they want us to find, then we can decrease our search range. We can decrease our upper bound. So we'll say high equals mid minus 1. And we will say lower bound equals the minimum math.min, lower bound, and mid. Otherwise, low equals mid plus 1. So for example, let's say they wanted us to find numbers from how many hay bales there were from 2 to 3. And we initially, our program started with this 5 over here. 5 is bigger than 2. So we can take our upper bound from 7 and shift it over to the left. Because 5 is bigger than 2, that means there are more hay bales over to the left side of 5 that could potentially be within the range of 2 to 3. So that's why we shift, say high equals mid minus 1. We also update our lower bound and do the same with, we do the opposite for low if the hay bale number is smaller. Now we can just copy and paste this actually, because we have to do 2 binary searches like Madhu said. We have to do 1 binary search to find the index for our answer, for the lower index for our answer. So for example, if they said find all hay bales between coordinates 4 and 6, we want to find the index of the first hay bale that is bigger than 4. But yeah, we want to find the first index. We want to find the index of the first hay bale that is bigger than 4, which is 3 over here for this 5. So that's what our first binary search does. And the second one will find the upper bound. So we just copy that. And again, once again, we have to reset our low and high variables. So we say low equals 0, high equals n minus 1, copy paste that. Some things we had to change are over here. We'll say if bales of mid is less than or equal to r, low is going to be equal to mid plus 1, upper bound. I'll copy that over here. Upper bound, upper bound. This should be math.max. This should be high equals mid minus 1. And those are the 2 binary searches. So this is, I'm about to paste it into the chat, but that's what you should have inside of your while loop. Now to actually print the answer, like Madhu said, it's going to be the upper bound, so the upper index minus the lower bound plus 1. And we can go ahead and run that. And it printed 2, 2, 3, 4, 1. And if you hit enter, 0. Yeah. So that's the solution to the hay bales problem. Once again, to go over it, we just want to find the number of hay bales between 2 ranges. So we do 1 binary search to find the smallest number bigger than our lower bound. And then we do another binary search to find the biggest number smaller than the upper bound. We subtract those indices that we found and add 1, and that's our answer. Are there any questions about that? So now we'll move on to we'll just discuss some other problems on the list of problems list. We won't actually get to coding them. Coding these 2 problems took longer than I thought they would. So let's take a look at this coast length problem. Or actually, I think we'll talk about fire, and then that'll be it for today. So I'll just go ahead and explain this problem. It's a really nice problem. You should try to code it by yourself after today's meeting sometime later. But basically in this problem, you're given a grid and you have this J over here, which tells you where John is. I think that's his name, where Joe is. So this J is where Joe is, and the F is where a unit of fire is. So Joe doesn't want to get burned by the fire, and he wants to escape out of this room. He can't go where the fire goes, but there's also a catch. Not only can he move, but the fire also moves. So for every second he can move, every second he can take a step of size 1. He can move 1 unit down, 1 unit up, 1 unit to the right or to the left, as long as it's not a wall. And these pound symbols over here represent walls. So in this example, you can see in his first step, he has to move down because he can't go onto the 2 walls over here and he doesn't want to walk on fire. So he's going to go down. The fire also moves at the same speed as Joe. Every second, the fire will move one step down, to the left, up, or to the right. And this is a really, really fun problem where you're given this room where Joe is, and there could be more than one fire, and you have to print whether it's impossible for Joe to get out. And if he can get out, you have to print the shortest amount of time it takes for him to get out. So we look at this first example over here. In the first second, Joe will move over here. Then the fire will spread to two positions. Now the fire will be here, and it'll also be here and here after the first second. So Joe is good. The fire still hasn't caught up to him. He's over here. The fire is in these three squares. Then Joe moves here. The fire is now here and here. So it's taking up these 5 squares over here. And then finally, Joe exits and he's safe. So it took him 3 seconds to get out. That's why we printed 3. Or it took him 3 minutes. It doesn't matter. That's why we print 3. Over here, the fire, you can see it's kind of sneaky. It's guarding the exit. So these are the 2 exits that Joe has to leave the room, but the fire is right on the corner. So in the first second, let's say Joe goes down. Joe goes down, the fire will move here and here. So Joe will he'll get hurt if he goes here. He can't go there. If Joe moves here in the first second, the fire will also move there. It's moving to all places that are reachable in one step every second. So it's going to be too late and Joe cannot exit. So that's why they print impossible. Now this seems like a pretty tricky problem, but it's actually not that tricky once you think about it. So what are some initial observations that you have? They can be very general observations about the problem. Maybe not about how to solve it, but anything about the problem. You can type them into the chat or unmute yourself.
I'm thinking that we can keep track of where the fire is going along with where Joe is going, and then we can do like the BFS for fire like at the same time as we're doing Joe, but like do the fire one before Joe, because let's say, because the fire is going to be there like when Joe gets there, right? So what we want to do is we want to check if the fire is there by the time Joe gets there, and that's kind of what I'm thinking about this.
Yeah, that's really good. That's part of the solution. So what Madhu is saying is do a BFS to find where the fire goes and maybe how quickly it gets there. And then when you're doing a BFS for Joe, because we already know how long it takes the fire to get to that spot, we can tell whether Joe gets there or not. So that's the solution in a nutshell. I'll go into more depth about it. So we'll take a look at this first example. So in this first example, we'll start by doing a BFS for the fire, and we'll keep track of the shortest amount of time it takes the fire to get to that position. And once again, this is literally what we covered in one of our previous meetings. You could copy and paste the code with a few modifications, it would work. So you need the shortest number of steps to reach each of these positions. And once we have this, oh, here, let me annotate this. Let me take a screenshot. So for example, well, actually, okay, here, this is good. So let's say we have Joe sitting over here and we have, I don't know what happened. Let's say we have the fire over here next to him. So what we'll do is we'll do a BFS and find the shortest amount of time it takes the fire to reach each square. So how long does it take the fire to reach the square over here where I'm hovering over? It takes
I think
it,
just all
yeah.
the nearest.
Yeah, it takes the fire 1 minute to reach these squares, 2 for these ones, and then 3 for others, and so on. And you can see it kind of fans outwards. 3 would be, all of these squares would take the 3 minutes to reach for the fire, and so on. So once we have constructed this 2D array of how long it takes the fire to get there, the idea is we do a BFS with Joe. And then we do a BFS with Joe, and it takes, how long does it take him to come here?
One because it's right next to him.
Yeah, it takes him 1 minute to come to these squares where I've drawn a purple circle. And the idea is that now that we know how long it takes the fire to get there, all we have to do is check how long it takes Joe to get there to determine whether he can go to that square. So over here, it takes Joe 1 minute to go to the square. It takes the fire 2 minutes. That means he can move to the square and be safe. So these 3 squares over here are safe for him to go to because he gets there before the fire gets there. But this square, it takes him 1 minute to get it. It takes to get there, and it takes the fire 0 minutes to get there. So it takes him longer to get there than the fire. He can't go there. So that's the solution. That's how you would solve this problem. For each of the fires, you do a BFS, and you take the minimum amount of time it takes any fire to reach that square. So let's say we had a fire over here. Let's say we had a fire here. It takes this fire only 1 minute to reach this square. So instead of saying 2, you'd say it takes 1 minute for the fire to get there. Because we don't care which fire it is that goes to a square. We just want to know the shortest amount of time it takes any fire to go there. Then we do a BFS with Joe, check how long he takes to go to a square. If he takes longer to go to a square than the fire, he can't go there because by the time he gets there, the fire's there and he's going to get hurt. So you can only go to a square if he can reach it before the fire. And that's how you solve the problem. This is really fun to code, and it's also a pretty fun problem when you think about it. Like you have this guy in a room, and then he has to try to escape, and then you also have fire and some walls and things. So this would be cool to code if you have some time. But yeah, are there any questions about that solution? Well, thank you for coming to today's meeting, and we hope you had fun during your Thanksgiving break and during this meeting as well. We'll see you again next week. Oh, and one more thing, if you know anybody who's interested in learning Java, we have a Java course we're going to be doing over winter break. So you can just share this form with them and let them know that this is something we're doing for free.